Start our next talk by Professor Zhilan Feng from Purdue University. She is the Program Director of Mathematical Biology in the Division of Mathematical Sciences of the National Science Foundation, the leading academic expert in the field of mathematical biology and population dynamics and epidemiology. So her talk will be on implications for infectious disease models for heterogeneous mixing on controlled thresholds. Professor, the floor is yours, and you can start your talk. Thank you very much.
Thank you. So I'll turn off my video just in case. But first, I would like to thank the organizers for inviting me to give this talk. This is a collaboration. So this talk will include the many results from many papers. So I have co-authors to acknowledge that I'll mention their names when I talk about those results. But I would like to especially mention my long-term collaborator, John Glasser. He's at the CDC. So we have been collaborating for almost 20 years. So we have published many papers on this topic, particularly mixing, non-homogeneous mixing or heterogeneous mixing in infectious disease models. And we would like to present the importance of considering the non-homogeneous mixing in the disease models. So for today's talk, I will focus on this control threshold, how non-homogeneous mixing will have influence on control thresholds, and therefore the model outcomes. So here, the control threshold refers to the reproduction number, either basic reproduction number or the control reproduction number. So I have to include this disclaimer. Any opinions, findings, and conclusions expressed in this presentation are those of authors and do not necessarily reflect the views of the NSF or the CDC. Okay, so I go to the next one. Okay. So first, some background information for control measure interventions. One of the main methods is vaccination. So we're interested in identifying the population immunity threshold so that the disease is either under control or reduce the severity of the outbreak. And so very often we see that in homogeneous mixing model, which means that all individuals are identical, there's no difference. In those simple models, you can specify this reproduction number and this control reproduction number. Here, subscript V stands for vaccination, and P represent the proportion of the population vaccinated. And so you can find a critical value of P such that RV is less than 1, so which will give you the critical point PC written in terms of the basic reproduction number R0. And if you vaccinate the population above this proportion PC, then you can either prevent an outbreak or reduce the prevalence or severity of the disease. But this kind of population immunity threshold may not work when the non-homogeneous mixing is important for any particular disease or for purpose of control. For example, if you want to vaccinate population for measles, then you have to consider age structure, right? Because the newborn or the young children, 18 months, will be recommended for receiving the vaccination. But sometimes you also consider supplemental immunization for adults. So in those cases, you cannot use this homogeneous mixing assumption, right? You have to consider population structure. I will show you an example, simple example, right? When you have even just two subpopulations, okay, with two subgroups, then the immunity threshold is not a single number. You can have infinite many pairs of critical values that can achieve the same effect, right? RV less than 1. And then they are not equivalent, those different pairs of immunity threshold, because you, for example, if you want to achieve a given goal, but you want to minimize the number of vaccine doses needed, right? Or you want to, for a given number of doses, vaccine doses, you want to minimize the reproduction number. Okay? Very often, this reproduction number, the magnitude of the reproduction number is associated with the severity of the disease. There are exceptions, but most times they are correlated. So I will show you an example why this immunity threshold is not usable in some cases. So here's a simple example. If you just consider two subpopulations, I'll talk a little more about the mixing. So epsilon here represent the preferential mixing, meaning that a given group, they have certain level of preference to mix with the other people within the same group. Okay, so here, if we assume that two groups have the same level of preference and the same population size, just to simplify this, some quantities and to see the importance of heterogeneous mixing. Okay. Suppose that two populations have different level of activity, right? Contact numbers, for example. So one group has 8, so you can have fixed a unit, for example, number of contacts per day or per week or per month. So one has 8, another group has 12, right? And if you want to simplify the model to consider homogeneous mixing and with just a single population, you probably were likely to assume that the average contact rate would be 10, right? You add those two and divide by 2. So 20 divided by 2 is 10. So if you do that, you have a simpler model, but then you get this critical value PC, for which the control reproduction number will be less than 1 here, right? But if you consider this heterogeneity, one group has 8, another group has 12 contacts, then this reproduction number, RV, is actually a surface of the two parameter, two parameters, P1 and P2. And then, so the blue plane is RV equal to 1. And so intersection, the curve, represent the pairs of P1, P2, for which RV will be less than 1 if P1, P2 are in this region, right? And then, so you can have infinite many combinations of P1, P2. And so they have different implications. Maybe some will have lower reproduction number and some will require fewer doses. So this threshold is not accurate anymore. So here's another just a simple example to show how this different P1, P2 combinations will produce different results. So the left plot is for the homogeneous case, right? So A1, A2 both equal to 10. And in this case, if you have this RV equal to 1, reproduction number equal to 1, the red curve, and you say you have a fixed number of vaccine doses, right? So P1 times N1, N1's population size 1, and P1, N1 plus P2, N2, that's the total number of doses. Okay, since N1 and N2 are equal, so this is constrained as equivalent to P1 plus P2. So this blue line is P1 plus P2 equals this value where RV is equal to 1, right? And so if you vaccinate the population above 74%, then you can achieve this RV to be less than 1 in this region. And any other pairs of P1, P2 will give you a higher value of the reproduction number, right? So this is the best. But if you have non-homogeneous mixing, A1 and A2 are not equal, then your curves no longer, you don't have the symmetry anymore. And if you look at this blue line, right, P1, P2, the sum is equal to 2 times 0.74. That's the same number of doses required. But in this case, you can actually find another pair, right, along the same line. So which means same number of vaccine doses, but your reproduction number is lower, it's 0.86, right? So this pair will be better than this threshold given by the homogeneous mixing model. And if you have, so here you want to achieve RV equal to 1, right, along the yellow dash line, that means that your vaccine doses will be lower because any line below the blue line will require fewer number of doses, right? So either way, the homogeneous threshold is not the best, right? And this is just for two populations. If you have more subgroups and you have a more many more combinations, then the question is which will be the optimum, right? And for that question, we use the so-called gradient approach, and I will mention more details about that gradient method later. So the simple example illustrates the importance of considering non-homogeneous mixing. Okay? And there are many examples included in the book we recently published, jointly with the Fred Brower, who passed away. But we finished this book in 2019. And so this is at his home, and collaboration with also Carlos Chavez. So if you're interested in more examples, you can find there. So now, if you have a more complicated populations, right, for different infectious diseases, and so I listed this example. This later on, I will mention a paper we just published for COVID-19, SARS-CoV-2. We use this diagram. So basically, you have n subpopulations, either by age, different age groups, or by different locations, right? And the subpopulations are linked through mixing, how people in one group will have contact with people in any other groups. And I will talk about examples of mixing later. And for each subgroup, in the case of COVID-19, you can have this transmission diagram as susceptible, exposed. And for infectious class, we have subgroups, subclasses, asymptomatic, symptomatic, pre-symptomatic, and hospitalized, and then disease death, and recovered, and also the vaccine class. Okay, if you have after vaccination, the individual can recover, but they can also receive booster doses here. They can have immunity wane back to the susceptible class, and so on. I will talk about that paper later in this talk. But first, that I want to show you a couple of examples to convince you why it's important to consider non-homogeneous mixing. Okay. The first example is we published in Lancet Infectious Disease in 2016. This is about a measles outbreak in San Diego School District. So I have a collaborator, again, John Glasser, I mentioned earlier, and then Sad Omar from Emory, and Philip Smith, also from CDC. And Lance Rodwald is from also CDC, and also he's with WHO also. So one of the important results in this paper is that if you consider homogeneous mixing, right, ignore heterogeneous mixing, so we have a data about the vaccination of different different schools in that San Diego School District. Different schools have different coverage, vaccine coverages. And some can be, unvaccinated, the population can be as high as 20%, and some schools will have higher coverage. So based on that coverage, and also 2 doses for measles with the given efficacy, you can calculate that the reproduction number, basic reproduction number for measles is 10.71. Okay? And for that, the population immunity threshold required is 0.907. So above 90% will prevent the outbreak. However, if you incorporate heterogeneous mixing, so we have different schools in a district. Some schools are larger in the city, and some smaller or in a rural area. So we have different characteristics. If you consider that mixing between different schools, then the basic reproduction number is actually 18.06, which is almost 70% higher than the reproduction number calculated from homogeneous mixing model. Okay? And that's a huge difference. And for that, the required immunity threshold is actually above 94%. Okay? In comparison with the 90%. So, so in this paper, we also examined different kind of control method to reduce reproduction number. For example, either increasing the coverage, vaccine coverage in the schools with lower vaccination coverages, or increasing coverage in the schools with the higher activities, higher level of connectivity, right, and so on. So when to see how those strategies compare. But I just want to point out the big difference between the models with homogeneous mixing versus heterogeneous mixing. Okay. Of course, this depends on your estimation model, the models and the estimation of parameters. So I will also mention later on how we estimate parameters. So that's independent of your model structure. Basically, we can I show you an example that we estimate the parameters force of infection from serology data. So the only difference will be mixing. Another example is the paper we published in International Journal of Epidemiology, and this is about the measles outbreak in China. We know that measles have been limited in many places in the world, but in China, the outbreak is the prevalence is still much higher. So they need design new vaccination strategies to accelerate the elimination of measles and rubella. So they invited John and I, me to work with the China CDC vaccination program to develop this vaccination strategies. So the co-authors, for example, Hao and Su and Ma, they are all from China CDC. And the lens is with WHO and again, John Glasser. So we work with the China CDC and published the paper, and actually the results of that work reported to the National Health Commission and Immunization Advisory Committee in China. And actually the results have a good sort of to represent our work has impact for their policy. And another example, this paper was published in The Lancet Infectious Diseases. This is about rubella, also in China, vaccination strategies. Again, we have people, some of the group of people, Su and Hao and Ma and so on from China CDC. And we have also people from US CDC, including John Glasser and the Lance Rollwood from WHO. So in those papers, we use this heterogeneous mixing with age groups and also the location of the 31 provinces in China plus those districts. And we use the gradient method. Again, I will talk a little more detail about the gradient method to identify which age groups will have a higher influence on the threshold, control threshold, reproduction number, right? So that means that we should target the effort on those subgroups, and also different provinces in China. So which group, which province, which location will have a higher impact, higher influence on the overall either basic reproduction number or the control reproduction number. Okay? And the main findings, so we actually made suggestions. If you apply the different coverages, right, using the gradient results, and how long will take if, for the elimination of rubella or the measles. And I would like to mention is particularly this so-called indirect effect via mixing. So when you vaccinate the group identified by the gradient method, okay, you not only reduce the prevalence or the measles cases in those groups, but also reduce the cases in other groups, right? The blue one represent the indirect. So you vaccinate, for example, the adolescents, right, under 50%, and you can reduce the number of infections, the orange line, okay, by a certain percentage, but you also reduce the cases in other groups, right, indicated by the blue line. So that's indirect effects. Okay, those kind of results you cannot obtain those results with a homogeneous mixing model. Okay, so those figures shows that if you target either adolescents or adults, okay, given same number of doses, right, you can have different coverages of subgroups, but you have a different effect in terms of reducing CRS. So those are examples. I just want to show you the importance of non-homogeneous mixing. Right? Now, how do we get those mixing, non-homogeneous mixing? So here, it is a simple example, the so-called preferential mixing. Okay? Basically, you have this parameter epsilon I, so I for subgroup I, right? Delta is either 1 when I equal to j, or 0 when I is not equal to j. Okay? So within the same group, I and j equal, then that group I will reserve epsilon I. So epsilon I is between 0 and 1. Epsilon I proportion of the contact to be with others in the same group. And the remaining proportion of the contact will be distributed among all other groups according to this, we call the proportional mixing, right? The total number of contacts is A times N. A is a contact rate and N is population size. And then the sum will represent the total available contacts in all groups. And then your contact from group I, that is with the group J, will depend on total number of contacts in that group. Right? So in for this kind of a mixing, your model analysis will be a little bit more complicated, but you can still compute the reproduction number, basic or effective reproduction numbers, and then explore the impact of group-related coverage of vaccination, how that will reduce the total effective reproduction number. Okay, so we published the paper. We're using the data for the activity level, the AI contact number. We use this Mosson et al. This paper about social contacts and the mixing patterns. So you can see the diagonal. So the lighter color represents a higher preference. You can see for a given age group, particularly younger group, they have a higher level of preference with others in the same group. Okay, but there are also the off diagonals that represent the preference of mixing between children and parents, and also some like grandparents and grandchildren. So, so we use this kind of mixing data to calibrate our mixing function that I showed you earlier. And this shows the comparison between the observed contact pattern and the modeled contacts after we estimate parameters using data. And then we will use those contact rates in the model. Okay? And their data shows, different countries, the contact patterns. And we can also consider the spatial mixing. So we use this for San Diego School District and the measles, the paper. So basically assume that the contact between different schools or different locations will decrease exponentially, right? With a parameter B that describe the connectivity. And we can also consider models with two-level structures. One say age, one represent the spatial locations. Okay, and the mixing can get more complicated, but we actually published a paper that described all different level of complexity, different functional forms for the mixing. And then so more when the mixing function is more complicated, then the computation of the reproduction numbers will also be more difficult. But you can always derive in the papers we published, you can always derive the next generation matrix and then numerically compute the dominant eigenvalue of that next generation matrix. And then you get the reproduction number. So this is about mixing. Now, so this slide shows several papers we published about the mixing and how the different mixing will affect your model outcomes. And now I want to show you how we estimate the model parameters. Okay, want to show to make sure your mixing, right, is your outcome, model outcome is independent of your model structure. Right? Basically, the parameter values were estimated using independent data sets. For example, serology data. Right? So here, if you have a multiple groups, location L for location, subscript L for location, subscript A for age, you have two levels of mixing. So what's important in this model would be this forced infection, okay, the lambda. The lambda connect different subgroups, right? And this lambda has dependent on several parameters. One is the activity level, which can be estimated from this survey data, for example, the mixing pattern, okay, independent model. And the beta is the difficult parameter. This is the probability of infection per contact. Okay, so that has to be estimated from serology data once you have the lambda, right? So we don't have ideas about the range of beta. And the C, so that again is from the contact data. So C and A are both estimated from contact data. And then once you have the lambda from serology information, and then you can estimate beta. Okay, so that's why the beta is independent of your the model structure. So here is just some quick example how serology data can be used to estimate the forced infection lambda. Okay, so the forced infection lambda, if you do this, uses an exponential function that will give you the probability of survival, right? The probability at age alpha, the individual is still susceptible, given the person is susceptible at age 0. And then the derivative of this survival function, the negative of the derivative, will be given by this function. Again, so the forced infection lambda is here. So suppose that we have information from serology that will give you the P, right? You identify first what proportion of population that has antibody, and then 1 minus that will be the probability still being susceptible. So from that data, you can estimate the lambda. Okay, and once you have lambda, you have A and a C, and you can estimate the beta. And another way to estimate the forced infection is to discretize the groups. For example, you can have every 5 ages in one group, right? And assuming that the forced infection would be same within one subgroup, and then you can discretize these parameters instead of a continuous function, lambda, a continuous function of age, and then you can again use serology data, the seropositive proportion of the population, and from that you can get your forced infection, right, as a function of the serology, seropositive, and the P is the vaccination coverage. And so that's the approach we use to estimate the forced infection and then infection probability. So now I'm going to quickly introduce to you the approach of gradient that we used to reduce the reproduction number. Okay, so we can consider 2 optimization problems, the Lagrange optimization problems with the constraints. So suppose you have fixed the number of vaccine doses, N for population size, kappa for vaccination rate for that age group, for that group I, and suppose the sum gives you a total number of vaccine doses required, right, available. And then you want to minimize the reproduction number. The reproduction number is a function of the chi, vaccination rate, the group dependent vaccination rate chi. And then you follow the methods of the optimization, find a solution. And it turns out that this gradient, so given the constraint, the blue dotted line, that's a constraint. And you want to find the combination of a chi such that the reproduction number is minimized. And we know that when you have a large groups, subgroups, you will not likely to get the explicit analytic expression for reproduction number, but you can calculate it numerically. So basically, you have all those counter curves for reproduction number. And that particular curve that intersected with the constraint line in a tangent way, and the intersection point, okay, and that gradient, that's a perpendicular to the constraint line, and that the gradient will give you the components of the gradient, give you the optimal combination of vaccination rates, chi1 and chi2. Okay, so we published a paper where actually will prove this gradient as an optimal solution in using multiple ways. So this is just one example to demonstrate. So last slide was for 2 subgroups. Now, if you have 3 groups, you have exactly the same kind of procedure, okay? And your reproduction number will be a surface. It's a function of the chi1, chi2, chi3 vaccination rates for 3 subgroups. And there's a constraint plane. And then the surface that intersect with this constraint plane in a tangent way, and that intersection point will give you this gradient direction, which will give you the optimal combination of chi1, chi2, chi3 that will minimize the control reproduction number. Okay, so similarly, you have more than 3 groups, and you can just follow the same methods. Okay, and in one of our papers, we actually also proved that, so given all other conditions fixed, right, you just vary the preference of the mixing, the group dependent mixing epsilon, and we can show that the homogeneous mixing model will give you the lower bound of the reproduction number. Okay, and then the isolated population, which means that those subgroups do not interact with each other. Okay, and that will give you the highest, the upper bound of the reproduction number. So this corresponding to epsilon equal to 1, right? Your preference is 1, and all your contacts will be with your own group. And this homogeneous mixing corresponds to epsilon equal to 0. So you don't have any preference. Right? Your mixing is random with any other groups. So those are 2 extremes. For any other epsilon between 0 and 1, you have this kind of monotone relationship, okay, in terms of the magnitude of the reproduction number. Okay, so now we're going to apply those methods to this COVID-19, the SARS-CoV-2. So we just published a paper in GTB recently in a special issue devoted to SARS-CoV-2 modeling. And this again, the joint work with John Glasser, and Mevan Vu is my PhD student at Purdue, and Jefferson and Katie are both from CDC, and Katie is from the Center of Surveillance, Epidemiology and Laboratory Services. So they provided this serology data for the entire US. So in this paper, we constructed our, the paper was structured as 3 parts. The first, we used a serological survey to estimate the model parameters, particularly the forced infection first, and then the transmission probability, as I showed you earlier. And then with that parameter values, we put in the structured model to identify the optimal vaccination strategies, right? You have a US 51 states, for example, and you have different age groups. You want to identify the age group and locations that will reduce the reproduction number the most. And then we compare the results if you follow the gradient approach versus what they actually used. Right? For example, in US, the vaccinate the elderly first, 65 and above, and then other groups, and also the healthcare workers and so on. We'll compare that approach with the strategy identified using gradient. And another example is uniform vaccination. So there's no difference. Vaccinate everyone at the same, just randomly. Okay, so this slide shows the serology data. They have different sources, different way of collecting those data. And from those data, we can estimate the force infection. So I'm not going into detail here. This slide shows, I showed you two methods, right, to estimate force infection. One is using this continuous function, one's to discretize the subgroups. So this the second one, okay? You have two indices, I and J. One is for age groups, one is for different states. And you can, so the surface shows the serology data. And then from that data, so data has age structure and the different states, right? Different time points too. And then you can estimate the force infection lambda. Okay, and actually this will be for different time points from the data. And then, this is another approach, right, to estimate the force infection. And then from the force infection, you can estimate the beta, probability of transmission per contact. And then we apply those estimated parameters in the model. So this is the model I showed you earlier with the 4 sub stages for the infectious stage. There's a symptomatic, asymptomatic, pre-symptomatic, and hospitalized, right, for all 4 I classes. And this slide shows the 4. A for asymptomatic, S for symptomatic, P for pre-symptomatic, and H for hospitalized. And the A, plot A, shows the reproduction number for the country. So you have a meta-population reproduction number. That's a sort of summation, the weighted summation of all sub-population, right? The 4 sub-population is a weighted sum of those reproduction numbers. So here, this slide shows the 4 sub-reproduction numbers. Okay, A subpopulation, or P, or S, or H. So we can see that the RA has higher values, right? 1.5, for example, here the maximum is 0.6. So that just shows that for asymptomatic subgroups, those secondary infections, right? They have a higher level of contribution to the meta-population reproduction number. Okay, and that's what this slide shows. The different lines correspond to different regions, right, based on the HHS region, right? I didn't label here. And this slide shows contributions from the gradient approach computations. So top 2 plus for the basic reproduction number R0, and the bottom 2 is for the effective reproduction number R sub E. Okay, that's under the vaccination programs. And the A shows this contributions of different age groups. Right? So when you compute the meta-population reproduction number, so that's the largest eigenvalue of the next generation matrix. And the eigenvector associated with that eigenvalue will give you the contribution of each subgroup. Okay, for example, here you can see that the age group of 50 to 54 here will have a higher level contribution to the meta-population reproduction number R0. Sorry, here. This is for each subgroup reproduction number. Okay, This B shows the contribution. So basically the younger age groups, school age subgroups actually will have a higher level of contribution to the basic reproduction number. And the bottom two shows similar results, but it's for effective reproduction number. Again, you see the younger group for all different states, right? Different lines represent different region. So that's the information we can get from the gradient computation. So now we want to compare the vaccination strategies. One is what's actually used, right? They vaccinated the healthcare and other essential workers first, and people at risk of a severe illness. So that's the elderly. And then you move to younger and healthier subgroups, right? This is what actually used in US. And so the goal of that is probably reduce the number of disease deaths, right? And protect the more vulnerable subpopulation. But if we have a different objectives, for example, you want to reduce this the total number of infections more quickly, right? Then you probably can have a different strategy, and the gradient approach will provide that. Sorry. So this slide shows this gradient results, the result from the gradient computation. So for different states, for example, you can see the contribution of each state to the net population reproduction number. And you can see that California has the highest, right? So gradient gave you the different the components of the vector. And the component represent the contribution, right? That here California has the highest contribution. And in terms of age groups, again, we can observe that the younger age group will have a higher level of influence on the meta-population reproduction number. And so the different bars correspond to different states. Okay, so if we follow the gradient approach, then we'll probably target those subgroups of population in terms of the vaccination priority. And this slide shows at the 4 consecutive weeks in January 2021, first, second, third, and fourth weeks in January, based on the vaccination that was actually used, the vaccination programs, and you can see how the contribution for different age groups will change as in different weeks in January. Right? But you can expect that you have still this lower contribution from elderly because they were vaccinated first. And so as I mentioned, that we actually compared 3 different vaccination strategies. One is what's actually used. One is the strategy based on the gradient computation, and one is if you just vaccinate everyone without difference, without considering different age groups or different locations. And the results, some part of the result we can is shown here, right? So those bars shows the absolute difference. Basically, you have 3 strategies, right? The lighter yellow for actual vaccination strategies, and the brown for gradient approach, and the blue one is for uniform. And you can see what's actually used, the strategy, the lighter yellow, they are not as good as for the asymptomatic class, right, we have 4 subclasses: asymptomatic, symptomatic, and hospitalized, and death. So 3 infected classes and 1 disease death. And so you can see for the asymptomatic class, actually the gradient approach will reduce more, right, the cases than what actually used or the uniform. But for the hospitalization or disease death, we can see that what's actually used, they have the larger, right, higher difference. They reduce hospitalization more if you follow the method, the program is actually used. Also for disease death, right, the actual policy is better in terms of reducing hospitalization and disease death. But in terms of reducing the asymptomatic infections, the gradient approach will actually will be better. And this slide doesn't show the timing, right? How fast the number of infection can be reduced if you follow this gradient approach to vaccination coverage. Basically, you target certain age groups and certain states. Okay. So I think that's pretty much all I would like to mention today. Again, so optimal strategy depends on policy goal. So that's why we compare the 3, and depending on your objectives and the different methods will provide a better strategy to achieve the goal. I hope I made it clear today. So mixing is important, especially for certain type of questions you want to study. It doesn't mean that you always have to consider complex mixings, and sometimes, mixing probably would not make a big difference in terms of the question you want to answer. But in many cases, we do have to consider structured model with non-homogeneous mixing in order to answer the questions that we want to answer. I'll stop here and answer questions.
Thank you very much for this great talk. For people who are online, they can raise their hand or write their question on the chat. So is there any question?
Hi, this is Ed Thomas. Thank you for the really nice talk. One thing I was wondering, in addition to looking at the effect on the reproduction number or the effective reproduction number, have you also looked at these different scenarios or summarizing these different scenarios in terms of the epidemic final size?
Yeah, that's a very good question. Actually, we get that question often. In one of the papers, we actually show that they may not be consistent in terms of you reduce reproduction number doesn't mean you're going to reduce the final size, right? But in most cases, they are consistent, right? If you reduce reproduction numbers, you will automatically reduce the final size. But for final size, it's really it's not easy to derive. Even for simple models, in a book we co-authored with Fred and Carlos, we talk about the connections between the final size and the reproduction number, right? Most time you see the monotone function, sometimes you don't. But even in a very simple case, your final size given by an implicit function, right? You don't get the explicit formula. So it's very hard to, when you get a more complicated mixing, very hard to investigate how different strategies will, whether they decrease or increase the final size. But thank you for the question.
Well, thank you very much.
Is there any other question? So I have a question regarding the mixing modeling. for the infectious diseases like tuberculosis with reverting back, does it change a little bit? Is it like a challenge for a mixing modern approach
Right.
in this kind of models?
Yeah, for tuberculosis, so this kind of mixing we derived is for what's called a respiratory, right, infection. So basically through direct contact, close distance, right, close contact. But tuberculosis is the similar thing, right? You breathe in the droplet that containing bacteria, and then you may get infected, right? So I guess depending on your questions, for tuberculosis, I'm not sure if you consider vaccination as a control measure. I don't know if that's age dependent or is, but certainly the spatial heterogeneity is important, right? For example, US has a lower prevalence, but some high prevalence countries, you would have immigrants, right? They come into the country and they contact with the local residents, and then they can, increase the local prevalence, right? So and then they probably very likely those immigrants have preferential mixing, right? They probably tend to have more contacts with the others, they're similar groups, and then the residents. But if you do have that kind of information, you have this knowledge about non-homogeneous mixing, then it's probably important to consider. If you, for example, you want to reduce tuberculosis by treating people earlier, because we know tuberculosis, in fact, latent period is very long, right? And a very small, like about 10% of the infected people will develop an active disease, right? And when people have a latent infection, they don't show symptoms, they don't know they're infected. But once they develop disease, the treatment will be harder, more difficult to take a longer time. So if you can identify those latent infections and treat them earlier, then you can first easier to get cured. I mean, I don't know if 2% cured, you are gonna get relapse or reinfection, but also you reduce the chance of developing active disease. And in that sense, you can also reduce the overall prevalence level, right? So it may be important to, if you have a limited resources and you want to identify latent people, maybe you can identify which subgroup you should target, right, given limited resources, right? And in that case, probably non-homogeneous mixing can be helpful. I'm not sure does that answer your question?
Oh, yeah, sure. We have another question from Professor Olsen.
Thank you. Interesting talk. This is not so much a mathematical question as more an empirical or applied question, which is, if you had your druthers, if you could choose to suggest to CDC or the National Center for Health Statistics in the States or somebody else, what kinds of heterogeneity do you think are most important for COVID? For example, in Canada, there was quite a bit of discussion about essential versus non-essential workers, or the fact that some parts of the population, lower income members, you were talking about immigrants, tend to live in more crowded housing kinds of circumstances. So those would be other dimensions than just age or general location.
Yeah, another very excellent question. Especially when you mentioned this in social economic, for COVID, it's very important because we know the COVID affected people, different subgroups disproportionately, right? And also people's behavior, different subgroups, people will have, for example, if you have lockdown, the people have a low income, they cannot afford staying at home, they still go out in the work, right? And then the people lose their houses, and then they will live in a more crowded shelter or facilities, and they will increase the prevalence, and then it will cause more problem with economics. So this is kind of interactions and that will affect the pandemic. So actually, it will be really interesting to consider a model that incorporate those factors explicitly. It's really important. Actually, you can speak for the NSF. Early this year, we announced a new funding opportunity, the title Incorporating Human Behaviors in Epidemiological Models, right? So we announced that in March, we got a huge response. Many teams submitted the pre-proposals. For that funding opportunity, we require the team to include the scientists from both mathematical sciences and social behavior economic sciences. And so they want, the goal is to improve the existing models, epidemiological models, so that it can provide more reliable evaluations of control measures and provide more a guidance for policymaking or forecast of future pandemic. And so it just shows that human behaviors or those social economic factors can be very important factor to consider, and that most likely, I haven't done work on that kind of research, but you can expect that the models can provide different kind of outcomes. So it is important, but to convince CDC or policymakers whether your suggested strategy is applicable, and that's a different story. I hope that answers your question.
Thank you. There is another question.
Thanks for the presentation. So my question would be on the mixing.
Mm-hmm.
And I think from the slide that showed the R naught, we had like R naught equals 10 point something for, I'm not sure if it's the homogeneous or I think the heterogeneous was kind of higher, 18 point, yeah, that. Yeah, so what would you regard as the implication of having like close R naught? So for instance, say if you had like 10.71, and then for the heterogeneous mixing, you had like 10.8 something. So would you consider the closeness to be a function of the parameter estimation, or does it mean that the kind of mixing is not important? What would be the implication? Thank you.
Yeah, thank you for the question. Actually, as I mentioned, the model, the parameter estimation is an independent model. So we use, for example, the one example is using serology data, right? That's independent model. You estimate the most important parameter, the probability transmission per contact. And then, so you would apply that in the model. I can show you example, right? So in this example, everything is the same. The only difference is the whether you consider homogeneous mixing or non-homogeneous mixing, right? You keep all other parameters the same. And when you do that, this is a very common, like people do that, right? You have a different level of contact rates, and then you say, okay, if you want to simplify a model to consider single population, I'll just take an average of the contact, right? So all the parameters, the other parameters stay the same. Then you can see that the model can have different results, right, in terms of reproduction number, effect of the vaccination coverage. So in this, in this example, again, so everything's the same except this mixing function. If we consider all the schools have the same activity and same kind of contact rate, or you use the also same the vaccine coverage, right? But if you use the data, a lot of schools, for example, if they have a personal belief exemptions, for some schools, the parents do not allow their kids to get vaccinated because of personal beliefs, then they have a higher proportion of students that are unvaccinated. And you have to consider that in order to identify, what is the best strategy? How do you increase the population threshold and to lower the chance for the measles outbreak? So you have to consider this non-homogeneous mixing. Sorry, did I answer your question?
Yeah. Yes, thanks.
Thank you.
Thank you very much. Is there any other question? So thank you very much, Professor Feng, for this